Hi, I'm Mikael Vidstedt. I run the Java virtual machine team at Oracle, and I'm here today to talk to you a bit about Flight Recorder, some exciting functionality we've been working on for a very long time. With me today, I have an expert, so we want to hear from you. If you have any questions, feel free to use the Q&A, the chat, and ask them, and we'll do our best answering them. There's an expert in the background there. And at the very end of this presentation, if we have some time, we will also answer some questions live on top of that. I've been working with Java my whole career, by the way. 20 years of really exciting functionality. So hopefully you'll find this presentation interesting and find something that you can go and have a look at afterwards. This is our safe harbor statement slide. It basically says that you should not base any important decisions on what I'm about to tell you about. So just keep that in mind. So let's say that you have some really business critical application or service that is running somewhere. And obviously it's important for you that this is up and running 24/7, constantly on, constantly running, because that's how you make your money. One day, and it's probably a Saturday, and it's probably 2 to 3 a.m. in the morning because, well, it needs to be inconvenient, right? You have an SLA breach. Something isn't working the way it's supposed to. Either you get an error message or things aren't performing as well as they should, or something goes wrong, right? So what do? Well, you go in and look at the data you have available and you try to figure out what's happening. And unfortunately, you find that the logs, the data you have collected, is not enough to actually diagnose this. You're not getting the data you need. So what do? Well, it's tough, right? But one of the things you can do is to go in and add information. So you add some logging information so that at least next time this happens, you have more information available. So you do that, you put it in production, and you wait. And nothing happens. So, and unfortunately, this additional logging, you had to add it in a place where it actually it has an impact. There's a performance overhead, or it's costing you in some way. Maybe it's using more CPU or more memory, and now it's actually costing you to have this code in there, and it's not finding any real issues. So what do? Well, at some point you have to make the tough decision. Should I leave it in there, or should I just disable that logging? And at some point, you probably will end up having to disable the logging again. And guess what? Someday, and it's probably a Saturday, and it's probably at 2, 3 a.m. in the morning, the same SLA breach happens again, and now you're back in the vicious circle. So what do? Well, the flight industry has sort of already solved this problem, right? There's a device, it's called a flight recorder. It's built into the airplane, and it's capturing all this low-level, detailed information. You don't know that, or you don't care really that it's there. It's just a natural part, right? It's there in the background, and if you need the data, it has collected it for you. So if you run into an issue, you can go back and look at the historical data and get all of that detailed information that you need in order to troubleshoot and diagnose things. And that is pretty much exactly what we've done in the Java runtime, and what I will spend the next 30 or so minutes talking about. The agenda looks something like this. So I'll talk about, on a high level, what JDK Flight Recorder is. I will touch on JFR or JDK Flight Recorder events and the APIs that come with JDK Flight Recorder. Events turn out to be very central to how JFR works. So I'll spend some time talking about that. I will touch on performance and why this functionality has been built and designed in a way so that you can use it in production. And finally, I'll talk a bit about how you can get started using JFR and show you a couple of demos on, basically how it works, to give you a feeling for how all of it hangs together. So starting on a high level, what is JDK Flight Recorder? So JDK Flight Recorder, or JFR for short, I'll be using JFR interchangeably throughout the rest of this presentation. It's an event-based tracing framework that we built into the Java runtime. So a lot of words there, but basically it's a central part of the JFR is the concept of events, and I'll touch on that in a few slides, what exactly an event is. But the nice part about it is that, again, it's built into the Java runtime. It turns out that in the Java runtime and in the Java virtual machine, we're already collecting all kinds of interesting data, and we're using that internally to base decisions on. So for example, we're deciding which methods should we spend time JIT compiling, because those are executed a lot. How should we optimize them? We're collecting information to drive the garbage collector. So when should we trigger garbage collection, and which parts of the heap should we look at? Those kinds of things. And that data is already being collected and used by the JVM. And what we've done with Flight Recorder is basically take that exact same information, piggyback on the fact that it's already being collected, and package it up and export it in such a way that you can use it externally to analyze what's going on inside of the Java runtime and your application as well. The fact that we're piggybacking on what the JVM and the Java runtime already does means that this has extremely low overhead. And as a matter of fact, we have designed it to have less than 1% overhead by default. And this means that you can and should use it in production. It's meant to be constantly on in production without having any overhead. And coupled with this, we also have APIs both for producing events. So the Java runtime has events that it emits and generates itself, but you can also produce your own events. But you can also consume the events and analyze and visualize them on the other hand. And I'll show you how that works a bit later. So events, as I said, are very central to how JFR works. And the events are produced by the Java runtime or the application. And again, I'll show you code on exactly how you can produce your own events. One of the things that also is central is filtering of event data, because it turns out that when you have this kind of low-level functionality that can produce a lot of data, you also need ways of filtering and only capturing and storing the data that is interesting and important to you. So there are different ways you can filter data. By default, the data is stored in memory, in thread local buffers. And the reason why I stress that is because we have designed it in such a way that the data is produced by the threads in thread local buffers first. That means that it's very cache efficient. There are no threads competing with each other, stepping on each other's toes. And that means that it's very efficient and has very low overhead. In the background, there's functionality then to take that data and store it in more, let's say, global data structure. And you can also optionally dump this data to disk as recording files. Typically, these end up with the JFR suffix. And you can pass them around, you can email them to your colleague and sort of post-process them after the events have happened. There are also various ways of analyzing and visualizing this data. I'll show you a couple of things you can use later. There's a command line tool, for example, where you can look at these events and use sort of all the power of the command line to analyze things. But there are also graphical user interfaces. We have one called Mission Control that I'll show quickly later. And you can also write your own code or agents to process this. So that's on a high level. So let's look a bit more in detail what JFR is and how it actually works, and especially the events and APIs. So JFR events, as I said, are very central to how JFR works. And an event is sort of just a blob of data. It does have a few common fields. So this slide here lists the common fields for events. The first one is an event ID. That's a unique identifier for this specific event. Makes it easier to look at and find events and correlate them and things like that. An event has a timestamp, so when did it happen in time, so that you can obviously see where, did it happen on this day when, my SLA was breached and exactly at the time of the breach. Events have durations, or I should say most events have durations. So you can say this took 20 seconds, or for that sake, the HTTP request, for example, took 200 milliseconds. So there's a duration associated with the event. There's a thread ID. Not all events have thread IDs, but most have. So this is the thread that actually produced the event, that executed the operation or processed the HTTP request or whatever it is. There's a stack trace ID, and basically what the stack trace does is help you obviously see where in the code this happens. The fact is that instead of embedding the full stack trace in the event, we instead just embed an ID, and then on the side we have the actual stack trace, because it does turn out that many or even most stack traces are the exact same. So instead of duplicating that data in every single event, we have a single small compact ID describing the stack trace, and then a sort of a pool of stack traces on the side. So that's an implementation detail, but it helps keep down the amount of data that gets generated. And then there are, depending on the type of event, the exact event that gets generated, there are also event-specific fields or payload associated with events as well. This is still sort of abstract, so let's look at what that actually looks like in real code. So I'm going to show you how you can implement your very own JFR event. And the way you do that is by extending a type called jdk.jfr.event. And you do that in the sort of natural Java way. So I'm creating my own event here. I call it my event. It's not, I guess I don't have a lot of good naming conventions coming up, so I just picked my event. Hopefully you will find a better way of describing your event, but I'm going to call it my event. And that's all it takes. Now you have your very own JFR event. But obviously this is just declaring the type. So let's see how we can actually produce an event as well. So let's imagine that we have some kind of business logic. This do thing method here is really important to us. I'm not sure what exactly it does. Maybe it is processing that HTTP request or something, but it does something really important. And you want to wrap an event around this in order to capture more information about how long it took and all of those other interesting things. So the way you do that is by adding a few lines of code, and I'm going to step through them one at a time. So the first step here is that we allocate or instantiate one of these my event types. So now we have an instance of the type. The next thing we do is to call a method called begin on that. And basically what begin does is to capture the start timestamp. So it says, now here's where the event actually started. Then we execute our business logic, and when we're done, we call end on that event. That, perhaps not surprisingly, captures the end timestamp of the event. So now we have the start and the end. And finally, we call a method called commit. And this is what actually takes the event data and feeds it into that thread local buffer, the stream in the background that I talked about. Now, you might ask, why have a difference? Why have two methods? Why have both end and commit? So it turns out that if you don't call end, commit has your back. It will call end or capture that end timestamp for you. There are cases where maybe you actually do want to have some logic in between the call to end and commit. But if you don't, this is sort of what it would look like. So instead of calling end explicitly, you can just call commit instead. That's all it takes. So now you have generated your own event, and it's been streamed into the background there and is part of the whole event stream, and you can look at it later. But not very interesting in itself. Like clearly we now know that there was an event, but we don't have any business level data associated with it. So how do you do that? How do you associate more data with it? Well, it turns out you do that in the most natural Java way possible. You add a couple of fields to your own event. In this case, I've added a message and a value field. Please give your fields better names and the type as well. I just, called them that because, I don't know, it felt good at the time. So you declare the fields in the type, and when you generate the event on the right-hand side there, you just set the values of those events, of those fields. And as part of commit, the JFR functionality will take those fields and the values and put them in the stream in the background. One other thing you can do, and I'm not going to go into a lot of details around this, but one of the things I encourage you to do is to add some annotations to the event type and the fields here as well. The reason why this is a good thing to do is because it dramatically helps in the analysis and visualization of the events later. So as a matter of fact, the format that we spit out the JFR events in is actually sort of self-describing. By adding these annotations, you can provide a better user experience when looking at the field. So instead of just saying, that the type here is called, my event, you can actually say something more human readable. And there are other annotations that you can play around with and add as well that will, again, help with the user experience of looking at these events later. This slide here is not an exhaustive list of annotations, but it sort of gives you a feeling for some of the most important annotations that you can use. If you want to see the full list, it's documented in the jdk.jfr Java docs. Very good long description there, and that's also where you can find a lot of other good information about how JFR works and some of the details you may want to keep in mind when generating and producing your own events. So we looked at what it looks like to generate your own event, but as I mentioned, there are also events that are generated by the Java runtime itself. And this, again, is not an exhaustive list, but it gives you a feeling for sort of the stuff we're already collecting in the Java runtime. So it's everything from the environment you're running in. This is everything from like the command line used to start the Java instance, to the version information, which JDK are you running right now, which version is it, down to the minor and patch level. We capture information about the operating system you're running on, the kernel versions, things like that, and also CPU level information. So for the specific CPU I'm running on, what kind of features does it have? Not all CPUs are created equally, right? So we capture a lot of that information. We do capture information from the Java level, so sort of the library level of Java. This includes things like I/O, so which files are being written to, read from, network I/O, so which sockets are you reading and writing to. And we also do thread sampling. This is a very efficient way of seeing what execution is actually doing. So like, what are the threads out executing right now? This can help you get a much better feeling for where execution time is spent, and maybe if you need to go in and optimize things, for example, where should I spend the time, right? And then, as I mentioned, we piggyback on a lot of the functionality and the data that the JVM is already collecting. So some of the key things include things like class loading, which classes are being loaded, but also GC, garbage collection information. When do garbage collections happen? All the sort of details around how garbage handling garbage collection is handled and all that. And also JIT compilation, so which methods are being compiled, why, how, that sort of thing. In total in the runtime right now, we have something in the order of 150 events. This is growing, so we are constantly adding, looking at which places in the JDK it would be useful to capture more information from. So you should expect this number to grow over time. I also want to touch on event filtering. As I said, with the kind of framework we have with JFR, it's very easy to generate data, and it's very easy to generate arguably too much data. So one of the key things that we need to do is filter data in various ways. And built into JFR, we have a couple of different ways of filtering data. The first one is sort of the obvious one. You can filter based on the type of the event, or let's say the name of the event. So let's say you want to know about socket reads, then you can say include that event. Or if you don't want to know about garbage collection, for example, you can exclude that. The other way to filter is based on duration. And the insight here is that there is, depending on the type of event, but there's often sort of a threshold. So for events that are very short, you may not want to capture that information because those probably behave the way they're supposed to. But if we go back to the HTTP request example, if the HTTP request takes, let's say, 250 milliseconds to process or more, then something may be fishy. You may want to capture more information about that. So what we found is that the combination of type-based filtering or name-based filtering and duration is very powerful because it allows you to capture the stuff that is important without all the, capturing too much data that you may not be interested in. The other thing that is cool about JFR is the fact that since we're capturing data from all these different levels, everywhere from the application level down through the runtime libraries, into the VM, and even on the operating system side, you have a way of looking at data on all these different levels and correlate things. So typically what you will end up doing is looking at a high level. So you're looking at that HTTP request, and you see that it takes a long time. Well, in the next step, what you can do is look at, on the core libraries level, the Java runtime level in the libraries, what was going on at the time during this HTTP request. And maybe you find that it is accessing, a database over some socket or something. And then you may see that, that is where the problem is. That's where I should go investigate more. Or you go into the next level and you see that the JVM was performing a garbage collection. So maybe there was a pause time or something like that. So in many cases, you start from the top and you drive down and drill in as deep as you need to go to find the actual issue. But what about performance, you ask? I keep saying that the typical overhead is less than 1% and that you should run with this in production. But at the same time, I just showed you that you need to sprinkle this event decoration stuff in the middle of your business critical logic. Surely that can't be a good idea, right? So I'm going to show you why that is a good idea and why it works out. And this is going to be sort of a journey through how the JVM and the Java runtime does optimizations in the end. So let's go back to the example we had with the business logic. So I have my do thing, really important method here. It's doing my business critical logic. And as I showed you earlier, we have just decorated that with this JFR event creation stuff, right? And that looks good, right? But surely there must be an overhead. So let's look at what all of that does. So I talked about the fact that begin captures the timestamp. That sounds relatively straightforward. So we'll look at what that means in a minute. But surely the complicated thing must be that commit call. That method must do a lot of crazy stuff. So let's look at what commit looks like. And the first thing I'll say is that this is actually not what commit looks like. This is just pseudocode. For various reasons, we need to bytecode generate this at runtime, so it doesn't actually exist as a real method on the Java level. But if it did exist, it would look something along these lines. So take it with a grain of salt. So commit, the very first thing it does is some of that filtering I was talking about. So it does a check to see if this event is enabled at all. Because if it isn't, then clearly we don't need to do more work. We can just early out. If it is enabled, we go to the next level and we do filtering based on duration. So we look at the timestamps, we look at the start timestamp, the current timestamp, if we didn't already capture it with end. We calculate the duration, and only if the duration is longer than some threshold do we actually go to the next phase and potentially commit it. There are some final checks that are being performed, but in the very end we call that actually commit method down there. And that is what actually puts this event data into the event stream in the background. Now, I should say that this may look costly, but in the end it actually really isn't. The CPU is really good at speculating compares and branches, so going through this code is very fast. And even if you go down all the way to actually commit, the event is enabled and the duration is long enough. It is, as I mentioned earlier, just writing to a thread local buffer, and that is very efficient. It's striding writes, and that's something the CPU knows how to handle really well. So even if we go through all of this and commit the data, it will still be really fast. But let's go back to our business logic here and see what happens. And I'm going to show you what happens if you do not have JFR enabled, or let's say if the event at least is not enabled. We have a principle when designing features in Java, which is that you pay for what you use, which basically means that if you're not using the functionality, the overhead should be 0. And then obviously if you use it, we still try to keep the overhead down, right? But I'm going to show you what happens when you're not using JFR, or again, when the event is not enabled. So what will happen is that the JVM will find that this method is being executed a lot and enough to motivate optimizing it. And I will show you over the next few slides what is happening in the JIT compiler when it takes the code and optimizes it down to an optimized version, which is effectively sort of native code. I will update the Java code here in the slides, but that doesn't mean that it will actually go back and update the Java code in your source files, right? It's just a way to display what the JIT compiler does. So keep that in mind. The changes I'm making here, or that I will show you here, are just happening inside of the JIT compiler itself. So the JVM has a number of very powerful tricks that it can play when it comes to optimization. One of the most powerful ones is called inlining. And basically what that does is to look at a method, and instead of calling that method, it simply just takes the method and puts it inside of the method that was calling it. So in this case, we see here, for example, that begin is called. It's grabbing the timestamp, we sort of know that, but what does it actually do, right? And what the JVM will do is to inline that method. And it turns out that what begin actually does is to set a field called start time to the value of a method called now. So it's basically grabbing a timestamp and storing that in a field. Now, after having applied inlining once, we sort of do the same trick again. We look at the now method there and we sort of do inlining, but it turns out that now is special. It's special in the sense that the JVM knows about this. It's something we've taught the JVM to treat specially. We call that a Jvm Intrinsic. And basically what that comes down to is that the JVM knows how to grab a timestamp extremely efficiently. So it basically comes down to a single CPU instruction or just a few. So this is in the order of nanoseconds, grabbing that timestamp. Okay, so we've done the first stab at optimizing things. Let's have a look at commit. So we play the same trick. We inline commit. And I haven't inlined all the code here, but so I've only taken the first filtering call or if expression and inlined that. And that is checking again if the event is enabled. So I'm going to show you now what happens again when the event is not enabled. So basically what the JVM does is a similar trick. It looks at is enabled and it notices that the event is not enabled. So it simply inlines the actual false value in the code. And then we play our next trick, which is called dead code elimination. We notice that this code clearly isn't being can't be executed. It's false. It will fall away. So we dead code eliminate it. We can remove it completely. Okay, so it's starting to look promising. So we have a couple of lines left here. There's another optimization called Scalarization. And what we're piggybacking on here is the fact that that field, that instance E, is actually not used anywhere else, right? We're allocating it and then we're setting up the field, but we're not using it afterwards. And so what Scalarization does is to store, don't store the value in the field in the instance, just use a local variable instead. Nobody will read from E later anyway. So if it can't be observed, then we might as well have a local variable for it, right? And in the next step, we obviously see here that the allocation or instantiation of my event is now also dead. Nobody's using it, so we can dead code eliminate that. And in the same way, start time is not used. We can dead code eliminate that as well. And what you end up with is exactly the business logic you started with. So again, remember, this isn't something you need to do on the source code level. This is all handled by the JVM as part of the JIT compilation. But it's sort of a way of showing what the JIT compiler does in the background. And hopefully you will realize that you can use this, you can do this, you can sprinkle these events, generate events. And if you don't have them enabled, the JIT has your back. It will remove all that code and you will have zero overhead. And remember, even if you still have the events enabled, it's still very efficient because it's still just a few thread local stores in the background. If we look at bar charts, here's what approximately that would look like. So I'm comparing here JFR disabled, which as we saw has zero overhead, with JFR enabled. I should say obviously that this all depends on your application, all of that. Your mileage may vary. Hopefully you understand that, but just to give you sort of a feeling for the magnitudes here. So with JFR enabled, you can see that there isn't an overhead, but it's relatively small. It's in the order of what, like a microsecond or something like that. With log4j off, you can see that there is an overhead. It's not big, but it's there. But maybe the more important thing is that when you turn log4j on, you can see that the overhead is pretty tremendous, right? It's, magnitudes higher. And comparing that to Java util logging, you can see that even with Java util logging off, the overhead is actually higher than with JFR enabled. So just, again, sort of to get a feeling for the magnitudes here. Now, I've deliberately left a couple of question marks at the end here. So what do you think will happen if you have Java util logging info enabled, or for that sake, if you print stuff to system out and you store that to a file? Well, turns out I had to rescale the y-axis quite significantly. As you can see, all the sort of other bars here, they don't even show up anymore. The overhead is so dramatically much higher using those frameworks that it's without question, JFR is more efficient, right? And again, coming back to it, we have designed JFR to have approximately 1% or less overhead. And that means that you can use this in production without having to worry about it. So how do you use JFR? So these are a few of the key ways of controlling JFR. So there is a command line option called XX start flight recording. And if you run with that, it will start the recording in the background and store all this information in memory. And then you can dump it out later. You can also specify optionally a file name to dump the recording to when you start up the JVM. If you forget to start the recording, there is a way to start recording on an already running VM. So in the JDK, since many releases ago, we have a new command in the bin directory called jcmd. And you can use that to start the recording and also to dump or extract the recording from the running instance. So let me show you a quick demo of what all of this looks like. So here I have a very old dear friend of ours. It's a Java 2D demo that we've been dragging along for many, many decades now. And I'm going to show you exactly what I showed on that slide. I'm going to say start flight recording. And I'm going to say Java 2D demo. And I'm going to run that in the background. So what you're not seeing here is that it pops up Java 2D demo, which, with bells and whistles and things happening. But what you can also see is that the Java process said it's starting a recording and there's no limit. So it's using the default. And here's how you can grab the recording information. And I'm actually going to do exactly that. I'm going to run jcmd and I'm going to store the flight recording data from that process in a file called foo.jfr. So now we have, if I list the directory here, you can see that we have a foo.jfr. And this file has all the bells and whistles, all the data inside of it. So now you can go and analyze that using command line tools, graphical user interfaces, or things like that. So I'm going to show you what it looks like to use a command line tool to do the processing. And if I look inside of the Java home bin directory, I find that there is a JFR command nowadays. This has been there since JDK 12, and I'm going to use that. I have Java home bin in my path, so I'm going to use that to visualize or print out the information in that foo.jfr file. If I just run JFR, you will see that it gives me information about how I can start a recording, which we already did, obviously, and also some pointers to how I can use JCMD to extract the information later. And then at the end here, it shows a bit of information about the commands that you can use to actually print out information. So, for example, if I run print on the recording, it will just list all the events that got captured as part of running this Java process. And as you can see, there are quite a number of them. I can also, for example, print that exact same data out as JSON, and this can obviously be very convenient if you're using this in other frameworks or consuming it in other ways. This is, after all, a command line tool, so clearly it's limited by being a command line tool, but also comes with the powers of being a command line tool. So there are pros and cons. I'm also going to show you another interesting way. So what I've showed you now is how you can start a recording and sort of passively have it running in the background. And when something happens that you're interested in, you can dump the recording and you get all of that historical data. What led up to the problem? And you can go and analyze that. But one of the things that we have worked on over the last couple of years is something we call Jfr Streaming. And what that allows you to do is to access the data continuously on a running instance. Instead of having to capture the data, store it to a file, and then look at it afterwards, you can consume it continuously and act on it. And one of my colleagues has created a small agent here. So I'm going to run that program using a functionality called Java Agent. If you're not used to what Java Agent is, it's basically a way of saying, run this application. So we're going to run the same Java 2D demo, which reminds me that I need to kill the one I already have running. Run the Java 2D demo, and also in the same process, run this other thing, this agent. So it's running the exact same Java instance. And if I fire this up, what you'll see is that it will start producing data. So this is the agent printing out information. And what it does here is basically subscribe to the stream. So events are being produced into the stream in the background. And what the agent does is consume those very same events and visualize them in this top-like way. So you can see here, for example, that we're capturing information about the GC, some information about the CPU usage on the machine, which methods are allocating the most memory, and which methods are executing a lot. Where's the execution time spent? So this is something that happens continuously now, and you can get this information very quickly now and act on it. So you can say, for example, if my HTTP request takes longer than 200 milliseconds, capture a recording or print out this other information about what the GC did at the time. So it's more sort of active way of dealing with the data. So going back to the presentation, one of the other ways that we're looking at exposing and making use of this data going forward is to stream events over JMX. So the ways I've showed you of sort of producing and consuming data right now, or over the last few slides and in the demo, all sort of requires you to be on the same machine. But what if you want to access this data over the network? So this is functionality that we are working on right now, and keep your eyes and ears open. It's something that will come in the future. In case you're interested in looking at the code for the health report agent I just showed you, it's available on GitHub. The URL is there at the top, and I'm also going to include that in the Q&A slide later. So don't be stressed up if you don't manage to grab it. And I showed you obviously here the sort of command line or shell version of analyzing data. There is also a UI called Mission Control, part of OpenJDK, that you can use to visualize this in a more graphical and maybe user-friendly way. So worth keeping an eye on and using as well. So in summary, JFR is an event-based tracing framework that we've built into the Java runtime. and that means that it has extremely low overhead. It's designed by default to have less than 1% overhead and can be used in production. We have these extremely powerful APIs that you can use to both produce your own events, but also analyze and consume events on the other side. And we have many different ways, and this set is growing, of analyzing and looking at it. So I showed you the bin JFR tool that can be used on the command line. We also have the graphical user interface mission control, and you can write your own agents if you want to do more specific handling of the data. So with that, I hand over to Q&A, and I've included a few resource links here in case you want to read up and know more about what's happening. So question, you mentioned that the typical overhead is less than 1%. What are some of the key things that affect the overhead? So yes, I did say that the typical or default overhead is less than 1%. There's something called configurations or profiles that we have inside of JFR. And the default profile is tuned in such a way that it only enables events and captures information that we know will basically keep the overhead to less than 1%. There are other profiles. So if you, for example, want to include information about allocations or exceptions and things that happen a lot and that have very long stack traces, that is one of the key things that is costly. So grabbing the stack trace. As a matter of fact, grabbing a single frame of the stack trace is almost equivalent to the cost of generating an event without a stack trace. So that's just to get you feeling, right? So if you have many threads with deep stack traces, the overhead will be higher. But the default set of events that we have enabled is designed to be less than 1%. So you can dial it up and you can capture more information, but then you may not reach this 1% threshold. What use cases have you seen people use JFR for? Are you using it for the JDK itself? Yes, this is a good one. So as a matter of fact, JFR has quite a long history. It goes back more than 15 years, and it started out with a team in Stockholm that I was working in. We met up at the same coffee machine, developers, test people, sustaining or support people. And at the same coffee machine, we sort of discussed the issues of understanding what was happening inside of the JVM. It's such a powerful piece of technology, but like when something goes wrong or when it doesn't behave the way you want it to, how do you know, right? So we formed the idea that it would be useful to be able to extract this information in some way and package it up. And that's what eventually became JFR. So the obvious use cases we had in mind at the time were both the sort of support use case. So a customer is running something goes wrong. How can we get all the information we need to understand what led up to that problem? But also for developing the JVM itself. So like, how do you know if your optimization, the improvement you're making to garbage collection, for example, how do you know that that is having the effect you want it to have? So those are a couple of the things that we designed JFR for from the very start. Now, what we've also found over the years is obviously that, you know, we're exposing this so that you as a Java developer can use it to understand what's happening in your application, not just the JVM, but the application as well. And then one of the most interesting use cases actually we played around with recently is using it for testing. So in some cases, it can be very hard to get the information out of your application or library or runtime to see that the thing is actually behaving the way you want it to. And given how low overhead and how detailed information you can get using JFR, we can actually use that to drive testing itself. You run some operation and you make sure that the expected events are generated in the way you expect them to. And as a matter of fact, we've even used that to drive testing of JFR itself, which is mind-blowing in many ways. So lots of different use cases. How do I keep track of the progress of the JFR streaming over JMX work? And in general, I guess the question is like, how do you know what's going on in the JFR development land, right? And all the JFR work is happening in the open as part of OpenJDK. You can both subscribe to email lists. There's a JFR development list where we do all development. We publish something we call JEPs, that's short for JDK Enhancement Proposals. It's sort of a description of features, and there's one, I've linked to two of them here on the in the resource list. There's one for Flight Recorder itself, sort of core functionality, and there's one for the event streaming work that we did as well. So that those JEPs will give you sort of more detailed information about what's going on. Also, if you are curious and actually want to look at the code, all of the code is open source, so you can go look at it. We very recently moved over to GitHub. So now you can find the OpenJDK project on GitHub under github.com/openjdk/JDK, I think. And there all the code is available, and you can sort of follow along and see the changes we're making there. So those are some of the ways of seeing what's happening. The other thing you can do, and please do this, is go look at the builds we're providing. So we're constantly publishing both builds of the GA versions of the JDK, but also of early access versions. So for example, right now, JDK 16 is in progress, right? And every week we are publishing binaries that you can download and try out. And please do that. Please download them, make sure everything works, and provide feedback. What would you like to see in JFR next in the future? What would help you become more efficient? And how would you like to use JFR going forward? So with that, I think we're out of time. Up next, we have in this track a presentation by Stuart Marks called Collections Refueled, which is touching on the various Java collections we have in the JDK and some of the new things that are happening there. And in the other track, there's a panel called Ask the Java Architects. It is moderated by Sharat Chander, and we have a bunch of the architects on the Java platform on the panel. Mark Reinhold, the chief Java architect, Brian Gutz, who is the language and core libraries architect. I'll be there as well, and Ron Pressler, who's working, among other things, on the Loom Fibers project, is going to be there to answer questions as well. So please tune in, go click on the button and join for the next sessions as well. Thank you very much.